One. In this video I am going to explain the different branching instructions available in 8085 microprocessor. So let's start. So the branching instruction in 8085, what it does actually. So the different branching instructions is basically for altering the normal flow of the program executions. Now what is the normal flow and how it alters? These are the two things to be understood. Number one, the normal flow of a program execution is that always the microprocessor executes the instructions in a program one by one normally. So for example, as we know that the program is a set of instructions. For example, a program consists of, say, instruction 1, instruction 2, instruction 3, one by one, instruction 4, instruction 5, so and so forth. Say for example, up till instruction 10, instruction 1, 2, 3, 4 up till instruction 10. Now the normal flow of the program execution is that microprocessor will execute the instruction 1 first, then instruction 2, then instruction 3, then instruction 4, and so forth up till instruction 10. Okay. Now point is that how it does this normal flow of execution. So who is giving the sequencing? Okay. So for giving the sequencing of the normal flow of the program execution, there is a 16-bit register. Particularly I am talking about the 8085. In 8085 microprocessor there is a 16-bit microprocessor, a 16-bit register called program counter. So program counter gives the sequence of executions. So how it does, how the program counter gives the sequencing of normal flow of the program, or the sequencing the executions. So how it does, program counter, when suppose microprocessor is executing then instruction 1, right? Currently microprocessor is suppose executing instruction 1. While microprocessor is executing instruction 1, at that point of time program counter will hold the address of the instruction 2. So generally, not generally, always you write your program in memory. In case of 8085 assembly level program, you have written your program in memory. Memory means in the ROM or RAM. ROM is read only, which is monitor programs are stored, and in your user programs is written in the RAM. So in a particular slot of RAM, in a sequential slots, you have written your program. Okay. So since 8085 is an 8-bit processor, memory is also in each memory location. There should be the provision for 8-bit. So therefore, all the up and also all the opcodes in the 8085 is of 8-bit, and data is also 8-bit. So therefore, for each opcode and data, you need to have one memory cell or memory locations. So for a particular programs, the entire program has to be written in a sequential slot in a block of memory. Okay. So at the very beginning, the first address of the address of the first instruction is given to the microprocessor. Means actually given to the microprocessor means given to the program counter. Program counter will assist to the microprocessor. It will give the address to the address bus of the microprocessor. Then instruction 1 will be fetched to the processor, and when microprocessor is executing the instruction 1, automatically program counter will be incremented by 1. That means it will hold the address of the next instruction to be executed. So that's how program counter gives the execution, sequencing the execution. So once the instruction execution of the instruction was finished by the processor, then microprocessor will look into the content of the program counter, because already program counter is holding the address of the next instruction to be executed. So immediately after the finishing of the first instruction, microprocessor will get the address of the next instruction from the program counter. So then the second instruction will be fetched to the processor, and the processor is executing. Suppose processor is now executing the second instructions. At that time program counter is holding the address of the third instruction. Okay, so so and so forth. So that means in short, what we can say, that program counter holds the address of the next instruction to be executed. So that's how a program counter gives the sequencing of execution, and in normal flow it is always one after another, okay, one by one. So that is why program counter get incremented by 1. Now in case of the branching instruction, as I said, branching instructions alters the normal sequence. Okay, it alters the normal sequence. Suppose normally what happen, instruction 1, then instruction 2, then instruction 3, then instruction 4, and so forth, normal execution of a program. But when we say alter, that means it may be anything. Suppose instruction 1, then instruction 2, then according to normal flow instruction 3 is supposed to be executed, but I am altering the normal flow. That means from instruction without executing instruction 3, simply suppose goes to instruction 6 of the programs. So that means it alters the normal flow of program execution. And I hope you understood how it alters. How it alters, because program counter always holds the address of the next instruction in a normal sequence. But if I would like to alter it, that means what? Forcefully I have to enter the address to which it needs to alter into the program counter. Okay, so for example, instruction 1 executed, then instruction 2 executed, and after the instruction 2 it's supposed to execute instruction 3. Now suppose at that point I would like to alter the sequence. So in general, program counter, while executing the instruction 2, program counter is holding the address of the instruction 3 in normal sequence. So suppose I would like to alter it to instruction 5, that means directly go to the instruction 5. Then forcefully, by means of some instruction, I have to enter the address of the instruction 5 into the program counter. Because normally it does automatically. Program counter incremented by 1 after executing each instructions. So while I am trying to altering, so forcefully I have to enter the address to which it would like to alter into the program counter. So microprocessor simply looks into the program counter automatically. Suppose microprocessor program counter, it holds the address of the third instruction while microprocessor is executing second instruction, but forcefully I am entering and the address of the fifth instruction. So then microprocessor will ask my program counter that what is the next instruction. So program counter will give the address to the address bus of the microprocessor. So whatever be the address, my microprocessor will take that instructions. So instead of instruction 3, suppose you are forcefully entering the address of the instruction 5. So that means microprocessor is, after instruction 2, microprocessor is going to execute the instruction 5. So that means it alters the normal flow of program executions. So this is being done by the different branching instructions. Okay, so this branching instruction can be 3 types: jump, call, and return. So what it is? Number 1, that altering or the normal flow of sequence can be within the same program. As I mentioned in the just before, that suppose an instruction is of suppose a program is of 10 different instructions. So within that, if it alters, suppose instruction 1, then instruction 2, then instruction 3, after that it directly goes to instruction 5. So that means it is within the same program. Within the same program, it is altering the normal flow. That is being done by the instruction jump, in short JMP. The mnemonics is JMP. So the instruction is jump. So while the instruction is jump, it is altering the sequence within the same program. That means it jumps from one instruction to another instruction by neglecting or by suspending some of the instruction in between. Suppose from instruction 2 it jumps directly to the instruction 5 without executing instruction 3 and 4. Okay, so that is being done by the jump instruction. Second is, if suppose you are having a main program, along with a main program there is a suppose sub program. Okay, subprograms is written generally for some repeating task. In a main program, if you write again and again, you have to write that repeating task. So when there is required to have a repeating task, so that repeating task is always written in a subprogram, and that subprogram is called into the main program whenever it requires. Okay, so the subprogram is also a program. So in the main program, suppose in instruction 1, 2, 3, at 3, suppose it need to execute some of the subprograms. So that means the program control should move from this current main program to the subprogram. So that is also altering, because in the main program it always goes normally it always goes from one after another. Suppose at instruction 3 it need to execute some subprograms. So the program control means essentially it means the program counter. So program counter content should be the address of the subprograms. Okay, that is also altering. Okay, so this is being done by call instruction. So it is calling the subprograms. Okay, so that is the second category. The third category, suppose you are you are in a main programs, and at some stage of the stages of the main programs you are calling a subprograms. So once the purpose of the subprogram is being finished, then the program control should be returned to main program where it stops in the main programs. Suppose at instruction 1, 2 and 3, at 3 it calls the subprograms. So it calls the subprogram means program control moves to the subprograms. So in the subprograms it finishes the part of the subprograms or purpose of the or task of the subprograms. So once it finishes the subprograms, the program control should return from this ending of the subprogram to the main program where it stops. Okay, to where it stops. So that is being done by the return instructions. Okay, so there are basically three: jump, call and return. Jump is to jump or altering the sequence into the same programs from one step to another step, directly jumping. Otherwise normally it always executes one after another. Okay, then if you are calling, or if your program control needs to move to some another program which is say subprograms, then it is called. And when it needs to return from the subprogram to the main program, then it is returned. So jump, call and return. This set of instruction is very important for controlling the programs under set of the programs in 8085 microprocessor, because there is no such, since it is assembly language, no if else, no for loops. So this if else, for loops, all these things is being handled using this branching instruction only. Okay, now whatever it is jump or call or return, these three instructions can be conditional or unconditional. Okay, so first let me tell you about the unconditionals. So what is unconditional? Unconditional means without fulfilling any conditions, it may jump, it may call or it may return. Suppose at instruction 1, 2 and 3, at 3 there is a jump instruction, for example, 2 which will neglect the 3 or 4 say subsequent instructions and directly goes to say 5, 6, whatever. So without fulfilling any conditions. Okay, so whenever there is an unconditional jump instruction, it does not look for any condition, simply it will jump. How it will jump? Already as I explained, you are forcefully entering the address to which you are jumping into the program counter at the point where you need to jump. Similarly, call also unconditional call. That means suppose you are at the stage 3 of the program, main program, say at the instruction 3. Instruction 3 is suppose your call instructions, unconditional call instructions. So without fulfilling any conditions, it will call the subprograms. Okay, without fulfilling any conditions, it calls the subprograms. And similarly, the unconditional return, once the subprogram is finished without fulfilling any other conditions, it directly returns to the main program where it stops. So how actually return instruction executed? It resumes the content of the program counter where it stops. Okay, so that way conditional and unconditional, conditional jump, unconditional jump, conditional call, unconditional call, conditional return, unconditional return. So there are three such instruction, jump, call and return, and for each of these three there is conditional and unconditional instructions. Okay, next point, unconditional is okay, without fulfilling any condition it jumps or it calls or it returns. But when it is conditional, what is the condition? Based on what conditions it jumps or it calls or returns? As you know, in microprocessor there is only one register, what we know as your decision box of the microprocessor 8085, which is known as the flag. There is no other anything based on which we can fix or we can set some conditions. To set or to execute or to define some condition in 8085 microprocessor is only the flag registers. So how flag registers defines the conditions? So as you know, there are 5 flags in 8085: sign, 0, carry, parity, auxiliary carry. Okay, sign, 0, carry, parity, auxiliary carry. Out of which auxiliary carry, as you know, auxiliary carry is the middle carry. So middle carry means it is if a 4-bit carry is generated, then auxiliary carry flag is set to 1. Otherwise means if the middle carry is 0, then auxiliary carry flag is reset to 0. So we can't take any decision at the middle of the result, because 4-bit carry is the middle of the result. So we can't take any decision at the middle of the result. So you just discard the auxiliary carry flag. So rest 4. 4 means sign, 0, parity and carry. So based on this 4, there can be 8 conditions. Okay. So suppose after results you need to take the decision whether you are going to jump or call or return. So how you will take? Suppose after any arithmetic instruction or logical instruction or any instructions, if Z flag is set, then jump, then call, then return, that becomes a conditions. Okay, if Z flag is reset or if Z flag is set, if the carry flag is set, if carry flag is reset, if parity is even, if parity is odd, if sign flag is set, that means sign flag is set to 1, that means when result is negative. Sign flag is reset to 0 when result is positive. Okay, if sign flag set, then jump, call or return. If sign flag is reset, then jump, call or return. Okay, so like that accordingly we can have 8 different conditions depending on 4 flags. Although there are 5 flags, we can't take decision based on the auxiliary carry flag, because auxiliary carry flag is 4th bit middle carry. So we can't take decision at the middle of the results. Okay, so these only the decision making systems available in 8085 microprocessor. So therefore you have to take the decision whether that based on the Z flag set or reset, sign flag set or reset, carry flag set or reset, parity flag set or reset. So accordingly there can be 8 such conditions. So those are those conditions. I have put it as this. So conditions, conditional flag, comment, and this will come into the instruction format as in opcode. Okay. Then if conditions are say NZ, NZ means no 0. That means result is not 0. After some operation, any operations, suppose result is non-zero. So when result is non-zero, that means what? Z flag is reset. So the condition is non-zero. Try to understand. Condition is non-zero. Condition is non-zero means if the condition is true, that means Z flag is 0. Condition is true means Z flag is 0. Okay. Suppose next condition is Z. Z means these are the form of the mnemonics, and that's why it is written like non-zero, 0, non-carry, carry, parity odd, parity even, plus, minus. So non-zero means when a particular result is non-zero. So the condition given is non-zero. That means result is not 0. Yes, true. Yes, true means Z flag is 0. That means result is non-zero. Similarly, 0. Yes, 0. Z flag is set to 1. If 0, given condition is 0, that means some result after certain operation, arithmetic, logical, whatever operation, result is 0. Yes, if 0, then Z flag is set to 1. Similarly, if there is a carry, end around carry, 9th bit generated, yes or no, no carry means no. Result is there is after the operation there is no carry generated. The condition is no carry. No carry condition is true. Yes, true means carry flag is set to 0. So carry, then carry flag is set to 1. Similarly, parity odd, parity flag is set to 0. Parity is even, parity flag reset to 0. Parity even, parity flag set to 1. Similarly, a result is positive, plus, that means sign flag set to reset to 0. Result is negative, minus, then sign flag set to 1. Okay. So these are the different conditions based on the set or reset of the particular designated flag. We can take the decision. We can jump, call, or return. Simply, if it is a suppose conditional jump, you just put J here, that means JNZ, JZ, JNC, JC, JPO, JPE, JP, JM. If it is a conditional call, then CNZ, just put C, that becomes the mnemonics for that instruction. CNZ, CZ, CNC, CC, CPO, CPE, CP, CM. Similarly, if it is a conditional return, then RNZ, RZ, RNC, RC, RPO, RPE, RP, RN. Okay, these are the different instructions for conditional jump, conditional call, conditional return. And unconditional, it does not look into this any flag. It's simply jump, it's simply call, or it's simply return. Okay, so let us start with this jump instruction. Okay, so jump instruction, first let us see the unconditional jump. Okay, unconditional jump instruction. So the mnemonics is JMP. Okay, so as I mentioned earlier that how it alters or how it jumps, by essentially you are feeding the address of the instruction to which you need to jump to the program counter. So therefore you have to provide the address along with the jump instruction. Suppose there is a program where instruction 1, instruction 2, instruction 3, instruction 4, instruction 5, like that. At instruction 2, suppose you need to directly jump to instruction 4 without executing instruction 3. So at instruction 2, normally when you are at instruction 2, normally program counter holds the address of the instruction 3. So what you need to do, you need to forcefully enter this address to the program counter. So that address is of course the address of the instruction 5 if you are directly jump from 2 to 5. Okay, so that is the instruction format, JMP address. So jump to the address, this address. So obviously while it is jump, it should be the address within the same program. As I mentioned, jump is jumping within the same program. Okay. So it is a 3-byte instruction where this jump JMP is the instruction for which there is an opcode byte 1, and this, since it is an address is of 16 bits, so there are 2 bytes, byte 2 and the byte 3. Byte 2 is the lower byte of the address, byte 3 is the higher byte of the address. So the content of the byte 2 and the byte 3, actually what is happening while jump instruction is executing, actually practically what happens, practically this address will go to the program counter. So what is this address? This address is being represented by byte 2 and the byte 3 of these instructions. So the content of the byte 2 and the byte 3 of the instructions are copied to the program counter. In that point, means based on that point, we can say that this jump address, this instruction is a data transfer instruction. Then what happens, because this data means this address is moved to the program counter. Okay, so it is a type of data transfer, but it comes under the branching instructions. So that means what happens when this address moves to the program counter, means program count that the program control now transferred to the address provided by the byte 2 and the byte 3 of the instruction. So the control of the program control, that means the program control is transferred to the instruction whose address is specified in byte 2 and the byte 3 of the instruction. Or in other words, we can say that the next instruction after this would be to be executed is the instruction whose address is specified by the byte 2 and the byte 3 of the instruction. Okay. So looking at this, we can say that this is a 3-byte instruction. Byte 1 is the output, byte 2 is the lower byte of the address, byte 3 is the higher byte of the address. So machine cycle here is 3, t state here is 10, and the addressing mode is immediate. Why immediate? Because the operation actually performs within the processor is a data transfer. So this address is moved to the program. And where is the address? Address is immediate after the instruction. So it is immediate addressing mode instruction. No flag will be affected because it is kind of data transfer instruction. And in the instruction format there are 3 bytes. Byte 1 is the output. Output is 1100 0011, which is your C3. And the byte 2 is the lower byte of the address. Byte 3 is the higher byte of the address. So, output is this C3 hex. There is one more unconditional jump instruction, which is PCHL. Okay, another unconditional jump instruction, which is PCHL. So here you are not providing any address, but where is the address to which, because it is unconditional jump. Since unconditional jump, you need to load the program counter with the address to which you are jumping. So but here you are not providing the address. Where is the address? Address is to which you are jumping is already there in the H cell, only the H cell register pair. So this is again another specialty of H cell register pair. So how it is? Once the PCH cell is executing, the lower byte of the address which is there in the L register to the lower byte of the program counter, and higher byte of the address which is there in the H register are moved to the higher byte of the program counter. That means program counter is holding the address which is already there in HL register pair. Okay. So what is there in the HL register pair? HL register pair holding the address to which you need to jump. Okay. The content of the HL register pair are copied to the program counter. The control is transferred to the instruction whose address is specified already in a HL register pair. Or in other words, the next instruction to be executed after this instruction is the instruction whose address is specified in the HL register pair. Now since here it is address is already there in the HL register pair, you are not specifying the address, so it is a 1-byte instruction only. Okay. And machine cycle 3 is that 10. Addressing mode is register addressing mode because you are directly pointing the HL register pair. Here also flag affected none, and in this case the output is 11101001, which is E9 hex. Okay. So these are the two, JMP address and PCHL. These are the two unconditional jump instruction. Now come to the conditional jump instruction. As I mentioned, condition is being defined by the 4 different flags. Okay, set and reset. So together there are total 8 instructions. Okay, if non-zero, if 0, if no carry, if parity even, if parity odd, if plus, if minus. Okay, so therefore the syntax is written like this: J condition. Okay, the condition is given by this. Condition is given by this. Okay. So this is same as that of the JMP instruction. Only thing is here the given condition has to be fulfilled, then only jump. Otherwise, it will continue as the normal flow. Okay. J condition address if condition, that means if the given condition is true, say for example J and Z. Okay, J and Z, no 0. So what is the given condition? Given condition is no 0. That means after certain operation, if the result is non-zero, that flag is reset to 0. So if condition means If suppose it is J and Z, the condition is no 0. So what it will look for? It will look whether the Z flag is 0 or 1. If Z flag is 0, then only these things happens. So these things happens means it's the same as that of this only, okay, unconditional jump. So thing is that here it has to fulfill the conditions. If the condition is fulfilled, true, then these things happens. That means then program control moves to the address whose address is to the memory location whose address is specified by the byte 2 and the byte 3 of the instruction. So if the given condition is true, then the content of the byte 2 and the byte 3 of the instruction are copied to the program counter. Otherwise, it is remain unchanged and program control will continuing its normal flow. In other words, we can say that if the given condition is true, the control is transferred to the instruction whose address is specified in byte 3 and the byte 3 of the instruction. Otherwise, program control continues sequentially. So as like your JMP address, it is also 3-byte instruction. But as you know, in the JMP instruction, there are machine cycle 3 is the 10. But here also the same. But thing is that the machine cycle is 2/3, that is 7/10. That means if the given condition is not true, suppose you are executing J and Z, that means given condition is no 0. Suppose it is 0, the result is 0, that means Z flag is set to 1. Okay, but you have given the condition no 0, so that means your condition is false, given condition is false. So at that point, if the given condition is false, then these things should not happen. These things will not happen. That means the program control will not transfer. Okay, so at that point, when given condition is not true, then the machine cycle is 2, because the task is reduced to be performed. Task to be performed is reduced. But if the given and when the machine cycle is 2, then T state is 7. First machine cycle 4, second machine cycle 3. But if the given condition is true, then it has to jump, okay, to the address. Therefore, at that point, the machine cycle is 3, T state 10. Okay. Of course, addressing mode is immediate, flag of none. Then in the opcode 11CCC 010. Okay. First byte, which is opcode, second byte lower byte of the address, third byte higher byte of the address. Now this CCC comes from this table. Okay, the conditional table, this CCC. For no 0 it is 000, for 0 it is 001, for no carry it is 010, and this is fixed. Okay, this is fixed. So accordingly there are 8 conditional jump instructions. So these are the different instructions, J and Z address. So J and Z means if no 0. If no 0 means if Z flag is reset to 0. Z flag reset to 0 means result is non-zero. Okay. So if non-zero, then only program counter will hold the address which is specified in byte 2 and the byte 3 of the instruction. Otherwise, it will continue. So what will be the opcode? For no 0, it is 000. So 1100 0010, which is C2. Okay, C2 opcode. Similarly, JZ. JZ means if 0. So if 0, Z flag will set to 1. Then this will happen, and for that it is 0 0 1. So that means C A. And like that, J and C means jump on no carry, JC jump on carry, JPO jump on parity odd, JPE jump on parity even, JP jump on plus, JN jump on minus. Okay. So these are the different conditional jump instructions. Now come to the call instruction, second call instruction. So as I mentioned earlier, the call instruction, in case of call instruction, the program control will transfer to a subprograms. Okay, to a subprograms. So how it will transfer? You are forcefully entering the address, first address of the subprogram to the program counter. Okay. So jump instruction is jumping within the same program. Call instruction is jump to a subprogram. Okay, so the instruction causes the program to branch to a subprograms or subroutine, also called subroutine, whose address is specified in the instruction. Okay, before the control shift, now see, there must be a provision of returning back from the subprogram to the main programs while call instruction executes. Suppose that instruction 2, instruction 1, instruction 2, instruction 3, instruction 4, instruction 5, this is suppose your main program, and suppose that instruction 2 you need to call the subprogram. So that means you are suspending the current task of the main program at instruction 2 and you are executing, going to, you means I am talking about microprocessor is going to execute the subprograms. Okay, and once the purpose of the subprogram is finished, then it should resumes its main programs. Okay, so while program control moves to the main subprograms, how it is control is transferred? By holding the address of the first address of the subprogram to the program counter. Now since there is a provision for coming back from the subprogram to the main program, so before control is transferred, somewhere you have to store the current content of the program counter, then only you can resume, no? Otherwise it will lost the address where it stops into the main programs. So how it will store? It stores into some memory location pointed by stack pointer. So in that point stack pointer is used. Okay, so the instruction causes the program to branch the subroutine whose address is specified in the instruction, but before the control shifts to the new address by loading the program counter with the new address, this instruction causes the current content of the program counter to be saved on stack. That means stack means a defined slot of read-write memory whose address is pointed by the 16-bit register stack pointer. And as you know, the stack pointer always works in leaf order, last in first out. So therefore, so in the this is not unconditional, this is conditional call instruction. Conditional call instruction. So in that conditional call, this is unconditional. Unconditional call instruction. The instruction is call address. But call address means program counter will loaded with this address, but before loading this address to the program counter, it has to, the same instruction has to store its current content of the program counter into some stack. That means into some defined slot of read-write memory, that is RAM, whose address is pointed by stack pointer. Okay, so current content of the program counter is this PCL PCH current content. Okay, what is the current content of the program counter? Next, the program counter always holds the next instruction to be executed. So current content, suppose you are executing call, at that point program counter is holding the address of the instruction next to call address in the main program. Okay, so that current content means defined by the lower byte of the program counter and the higher byte of the program counter. Where you are storing? The lower byte you are storing into the memory location whose address is 2 less than that of the program counter. 2 less than that of the stack pointer. And higher byte of the program counter, current content of the program counter, you are storing into the memory address, memory location whose address is 1 less than the stack pointer. Why this is so? Because stack pointer works in a leaf order. Okay. And then you have means the same instruction has to decrement the stack pointer content by 2. Okay, just with an example I will just show you here. Suppose currently stack pointer is suppose 2050 currently. Okay, now in the 2050 minus 2, say for example 2056. So this 2056 minus 2, that means 2054. Okay, so in the 2050 you are storing PCL. Suppose your PC is, current content of the PC is, suppose current content of the PC is, suppose your say 2020, okay, 20 say 30 for example. Now in 2054 what will come? 30, then 2053 it will be your 20 higher byte of the program counter, then stack pointer is decremented by 2, okay, stack pointer is decremented by 2. So the stack pointer is decremented by 2 means current content of the stack pointer was 2056, then decremented by 2 means 2054, okay. So that how you are storing the address into the stacks whose address is being defined by the stack pointer. Stack means a defined read write slot of defined slots of read write memory. Now while coming back from the main subprogram to the main program, so then program counter will ask the stack pointer to give back its address, but stack pointer works in a leaf order, last in first out. So what is the current content of the stack pointer? 2050 now, okay. So while it comes back, it will give the address this 30, because it always works in a leaf order, last in first out, okay. So 30 will come first, then 20, as 30 is the lower byte, it has to come first, then your 20 is the higher byte, so it comes next, okay. That is why SP is decremented by 2, so that it maintains that leaf of things, okay. Hope you understood. So this is you see while calling, first it has to perform this part. After that it is same as that of the jump instruction. PC will be holding this address. Once PC is holding this address, that means program controller transferred to the subprograms, and it works in the it executing the subprogram. Once the subprogram is finished, then it will come back to the main program by taking the address from the stack pointer. Not the stack pointer. Stack pointer will point the memory where the address is stored, okay. So the higher order byte of the current content of the program counter are copied to the memory location whose address is 1 less than of the stack pointer, and lower byte of the current content of the program counter is stored into the memory location whose address is 2 less than the content of the content of the stack pointer. Then current content of the stack pointer is decremented by 2, then the content of the byte 2 and the byte 3 of the instructions are copied to the program counter. So lot many things has to be done, therefore that is why in this case machine cycle is 5, this state is 18. How it is? In the first machine cycle there are 40 states, second, third, fourth, fifth, 3 each, so total of 8, and it is a 3 byte instruction. For call there is a output, and for address this is 2 byte, okay. And this is immediate addressing mode as well as register indirect. Why immediate addressing mode? Because this address is immediately given with the instructions, immediately given after the instruction, which is copied to the program counter, but as well as it also performs this task, which is register indirect. Therefore it is immediate as well as register indirect addressing mode. None of the flag will be affected, and in the output instruction format there are 3 bytes. First byte is the output 1100 1101, which is CD. Output is CD hex, okay. CD hex. So next is the conditional call instruction. So conditional call, it will be again the same thing will happen. The same thing will happen as I explained just before, only if the given condition is true. Again, who is giving the conditions? Those 8 different conditions based on the 4 different flags: sign 0, carry, parity, sign 0, carry, and parity. Okay. So this, if the given condition is true, then only these things will happen, otherwise it will simply continue in the main program only, normal flow. So the same thing, these things as I have written here, all these things will happen only if the given condition is true. So if the specified condition is true, then all these things, same thing happens. Okay, so here also number of byte 3, but the number of machine cycle is 2/5. Why 2/5? Because if the given condition is false, then it need not to call, it will continue in the main program. So task being reduced. So therefore at that point machine cycle 2 T state 9. How it is 9? First machine cycle it is 6 T state, that is 6 period of clock, and 3 in the second machine cycle. And if the given condition is true, then it will do all the things. In that case 5 and T state is 18. Addressing mode same, immediate and register indirect. And in the instruction format the opcode is 11 CCC 100. So that CCC again from the same table, if 0 no 0, like that. So the address different instructions are CNZ, CZ, CNC, CC, CPO, CPE. Okay, CNZ colon non-zero. Non-zero means if the given if that flag is reset. Non-zero means reset. So if that flag is reset, that is 0, then this happens, otherwise it will continue. Opcode is C4 because 1100 0110 1100 is C in hex, C100 100 is C. 0100 is 4. So therefore C4 hex. Similarly CZ, CNC, CC, CPO, CPE, CPE and CM. Okay, so these are the different conditional call instructions. Now comes the your next is your return instruction. Return instruction. So return instruction is for returning back from the subprogram to the main program. So the unconditional return instruction is simply RET, return. So while returning, as I mentioned just before in the call instruction, that it should resume its. Okay, so in the return instruction, as I mentioned earlier, that the program control will transfer from the subprogram to the main program, that is it resumes the task in the main programs. So how it does? Because while calling to the subprogram, the current content of the program counter is stored in the stack, so it will resume it from the stack. So as I mentioned, as you can see with an example as I explained, so from the SP, from the memory location whose address is the current content of the SP, will go to the lower byte of the program counter. And one more than that, because program stack pointer works in the leaf order, so therefore one more than that of the current content of the SP goes to the higher byte of the program counter. And to maintain again in the same fashion of the SP is incremented by 2, because it should go back to its original position again. Okay, so the content of the memory location whose address is specified in the stack pointer are moved to the lower byte of the program counter register, and the content of the memory location whose address is one more than that of the specified in the stack pointer is moved to the higher byte of the program counter, and SP is incremented by 2. So here number of byte is 1, it is a 1 byte instruction. There you need not to provide any address, because address is indirectly specified by the stack. And number of machine cycle 3 is the 10, and it is register indirect. Addressing mode flag none, and opcode is C9 hex. Okay. Similarly, the conditional return instruction is the R condition. That means if the given condition is true, then only return. Otherwise, if the given condition is false, then it will not return to the main program. That means it will not resume its execution into the main program. Okay. So again same thing, if condition, these things will happen, otherwise nothing will happen. It will stop at the subprogram. The entire program will stop at the subprograms. Okay. So here is the number of byte 1, machine cycle as like the previous conditional instructions 1/3. So 1 when the condition is not true, in that case t state is 6, and if true then it will move, and our t state emission cycle is 3, t state is 12. Okay, so addressing mode is register indirect addressing mode, flag affected none, and instruction format is this 11CCC 000. So accordingly different instructions are RNZ address returned on non-zero. If non-zero, Z flag is reset. Okay. Similarly, RNZ, RZ, RNC, RC, RPO, RP, RP, RM. Okay. Okay. So next is the restart instruction. This is also a call instruction. Okay. This restart instruction is also a call instructions, but unconditional call and a specialized call. Here you need to understand. Okay, it will be same as that of the call instructions, like unconditional call address. What was the call address? Call address means it will program control will transfer from the main program to a subprogram. So call address. So that address is the first address of the subprograms. So program control will transfer from the main program to the subprograms. Okay, that is your restarting. So, but thing is that in the restart instruction, the address to which the program control will transfer is fixed. So when it is fixed, it has to be some monitor programs. Okay, monitor programs means some fixed programs, okay, which are already stored into the ROM, not in RAM. It is not user defined programs, it is monitor program. Monitor programs are the programs for some fixed task already written by the manufacturer. Okay, so these are the special unconditional call instruction. In this instruction, instead of an address, a number is defined, RST n. So what is this n? As I mentioned, it is as like unconditional call address. Instead of address, it is a, here small n is specified. So this small n, as I mentioned in the RST instruction, the subprogram is fixed, monitor program. So address is also fixed. Address is defined by n. There are such 8 subprograms, fixed monitor programs, for which this n is specified. So if n is 0, n can be 0 through 7, 0, 1, 2, 3, 4, 5, 6, 7. So there are 8. Now what is the address of those monitor programs which were stored into the ROM? If n is 0, address is 0, 0, 0. Okay, actually this n is being multiplied by 8. It is unknown already. So n is n into 8. Address is equal to n into 8. Okay, so 0 into 8, 1 into 8, 2 into 8, 3 into 8, 4 into 8, 5 into 8, 6 into 8, 7 into 8. These are the different addresses of different, so first addresses of the different 8 different subprograms. Okay, so it is same as that of the unconditional call, but it is a special call who instead of address an integer in between 0 through 7 is specified, an address to which it will call is n into 8. Okay, so the things will happen as that of the call only, as like call instruction only. The same thing will happen, but program counter in the call instruction is loaded with the address given along with the instruction, but here it is 8 into n. Since n is 0 through 7, so in binary it can be represented in 3 bit. 0 through 7 is represented in 3 bit, so that 3 bit is being designated as n. 8 into n. Okay, 0 0 0 for 0, 0 0 1 for 1, 0 1 0 for 2, 0 1 1 for 3, like that. Okay, the meaning is same only as like call, but instead of the address specified in byte 2 and byte 3 of the instruction to the program counter, it is 8 into n or 8 into small n, where small n is 0 through 7. Okay, so here is 1 byte instruction is equal to T state 12. Addressing mode immediate and register indirect. as like call, and opcode is 11NNN111. That means NNN RST0 it is 000, RST1 like that. So RST0 it is 000, opcode is C7, RST1 it is 001, RST2 it is 010, 3 it is 011 like that. So 8 different instructions. For your simplicity, what we can say that, as you know, this if you multiply 8 by any number, 8 is by in binary 0 0, sorry, 8 is in binary 1 0 0 0. Okay, since 8 is 1 0 0 0, so for because in this case address has to be 16-bit, no? So this 16-bit address can be of this form. You need not to multiply 1 again and again. It is, if you see, if n is 0, that means 0 0 0, so it will be address is 0 0 0. If n is 1, so it is 0 0 1. If you multiply 1 with 8, then it becomes in 16-bit, it becomes this, and in hex it is 0 0 0 8. Similarly, RST2 means it becomes 0 1 0. That means 2 into 8, which is 0 1 0, like that. So these are the 8 different addresses to which this RSTN instruction will call. Okay. So these are the branching instructions. These branching instructions are very much important. These instructions are used while you need to take some decisions. As like in high level programs, we do use these if else, switch case, and for loop, do loop, while loop, all those things here in Microprocessor 8085 has to be maintained with these only the branching instruction jump, call, and return. Okay, so jump conditional, unconditional, call conditional, unconditional, return conditional, unconditional. So these conditionals are always based on the 4 different flags. Out of 5, 4 different flags: 0, carry, parity, and sign. Accordingly, 8 instructions. And there is 111 conditional instructions, unconditional instruction, but in case of the jump there is one more unconditional instruction, which is PCH. And in call there is one unconditional call instruction, one more unconditional call instruction, which is RSTN, but in this case the address is predefined by n into 8, where small n into 8, where small n is 0 through 7, 0 1 2 3 4 5 6 7, which is predefined address. These addresses are the first addresses of some designated fixed monitor programs. For some purpose these are used. We'll explain these things, means where we use these monitor programs and all through programming later on. Okay, hope you understood. In my next video I will go through the stack, IO, and the machine control instruction. Let's stop here. Thank you for listening.